Welcome to the second installment of our lesson about the differentiation rule called the chain rule. This has everything to do with us finding the derivative and therefore the slope and other things of a function that is made up of two functions in a composition. And so we're going to investigate and look at this rule again with an example that we may have looked at one like last time, and then we'll apply this rule to other situations as well. So let's review what we learned in the previous video, and we'll state the rule two different ways, two different forms, and see how it's applied to a situation like what I've got down here. The example is, what if I wanted the derivative of the function y equals x squared plus 4 to the 17th? The options for finding this function's derivative are either A, we take time and expand this out, x squared plus 4 times x squared plus 4, and expand it all out 17 times, which would take a very long time, and then finally find the derivative of all that, or leave it in the form it's in and use what's called the chain rule. In the statement of the chain rule, it says, suppose that y is a function of the variable u, but then at the same time, u is a function of x, g of x. In my example, I can make this distinction. I've got y equals x squared plus 4 to the 17, but I can write that as two smaller, simpler functions. I can write it as y equals u to the 17, where u is the expression x squared plus 4. So now this satisfies the hypothesis of this theorem. Y is a function of u. Okay, so in other words, the formula for y involves the variable u. But now u is a function of x. So the formula for u is a function of x squared plus 4. So now what the end of the theorem is suppose y equals f of, if y equals f of u, then you notice if I were to combine this back together the proper way, it would lead back to the original expression. So in other words, finding the derivative of this entire original function would be finding dy dx, the derivative of y with respect to the variable x. And the chain rule says simply multiply the two derivatives, the derivative of this function, that's a function of u, times the derivative of u, which is a function of x. So it says take dy, derivative of y with respect to u, and multiply by the derivative of u with respect to x. So in terms of my breakdown, the derivative of y with respect to u would be, notice that there's just only requiring the power rule. The derivative of u to the 17 with respect to u is 17 u to the 16. And then du dx is the derivative of u with respect to x. This would be the derivative of x squared plus 4, which is 2x plus 0, or just 2x. So in my final answer, though, I would like the answer to be all in terms of x. So it would be 17 times, now I'll go back and put x squared plus 4 in where u is. So this is my derivative right here. There's some other ways we could write it, like 17 times 2x could be changed to 34x. That's all optional, simplifying. Okay, but then we definitely cannot bring anything inside of the 16th power. So here would be an alternate way to write it. Okay, now I also want to point out the second way of writing this rule. It's quite common to call the innermost expression function g, and then the 17th power in this example would be function f. Okay, so if I look at my final result here, the first part of my derivative was the power rule, 17u to the 16. but that was the derivative of the 17th power function. So that would be considered in this statement the derivative of f, but not f prime of x. It's f prime of u, and u is a synonym for that inside function g. So this is really f prime of g of x. And then when I multiplied by du dx, that was the derivative of g. So it's f prime of g of x times g prime of x is a identical statement to the first version up there. Okay. Now the way I was doing it here leads me to say, well, any of the basic derivative rules you already know can be transformed into what we call the chain rule version. So on your list of derivatives, in box number 2, it's got this, the basic power rule, which says, what's the derivative of any power of x, x to the n? And we know that rule now. It's n, bring the power down, and then decrease the power of x by 1, right? But that is only if the base of the exponent is x, the variable x. But in the previous example, we had a power function where the base was another function, x squared plus 4. And that leads us to what we call the general power rule, or what I would also call just the chain rule version of the basic rule. Okay, the general power rule is the chain rule version. Which is stated, what's the derivative of any function, any expression to the power n? And it's assumed that u is the placeholder for some other function, like x squared plus 4. Then all I've got to do is apply the regular power rule, bring the power down, decrease the power by 1, right? But this is u, not x, which means the derivative of u has to get multiplied as well. So again, this is like the derivative of the main function times the derivative of the inner function in u prime. So above here we have what I call the chain rule version of the remaining derivatives that you've already learned. Here's the chain rule version of the sine rule. The derivative of sine of x is the cosine of x. But here it is accounting for, what if it's the sine of something like sine of x squared? Then we use the chain rule because there's a second function inside of the sine function. And the rule would go, derivative of sine of u is cosine of u times the derivative of u. And so all the remaining statements on this list are just the chain rule version of a rule you already know. So for example, here number 7 says the derivative of e to the u. Well, the derivative of e to the x was e to the x. So if it's e to the something else, e to the u, then we use the chain rule, and it's e to the u times the derivative of u. Okay, I want to point out there's really nothing new to memorize here other than they all follow the chain rule. Okay, and that is you multiply by the derivative of the inner function at the end, all of them. Okay, so we're going to see some examples today using trigonometric functions and some examples using exponential functions. So on each slide, I'm going to work one out in great detail, and then I would encourage you to pause the video and try the other two yourself in the same way, but I'll write the answers to all of them after that. So to write each of these in the form of those differentiation rules, I like to substitute or call u the little function that's inside of the other one. So if u could be called 2x, I could then rewrite my primary function y equals sine of u. And so now that I want to find y prime, or dy dx, the chain rule says find the derivative of y with respect to u. That would be cosine of u. Multiply that by the derivative of u with respect to x, which would be 2. So finally, I want the answer back in terms of x. So my derivative of sine 2x is going to be cosine of 2x all times 2. Just so there's not any confusion about what can be combined and what can't, I would usually bring this coefficient, this constant 2, in front of the cosine function. That way, we certainly do not want to bring it in here and call this cosine 4x. That would be wrong. Okay, so this is the way we're going to write it. I would encourage you to pause the video now and look at the other two examples and try and differentiate or find the derivatives the same way. Okay, I've completed the other two examples on this page. You could pause it here and just examine them and compare them with what you wrote, and just verify that you can follow the same line of reasoning as the first one. Let's look at two additional examples where we have a trigonometric function, but it's used in a different way. This time I've got sine squared of x, and it's very important that you recognize this as the same or equivalent to finding the sine of the number x and then squaring it after that. Okay, so what's seen this time is that making the substitutions, we're going to call u sine x, and then the main function is y equals u squared, right? So my derivative for y prime is to find the derivative of y with respect to u, which is going to be 2u to the first, multiplied by u prime. And so I will fill in both those items. 2u is going to be 2 sine x. And then u prime is the derivative of u with respect to x. That's going to be the derivative of sine x, which is cosine x. So my derivative is already in a good way written 2 sine x cosine x. So notice this time this trig function was the inner function inside of the squaring function. Now this last one is interesting because I've actually got more than just 2 layers here. I would rewrite this for clarity as the cosine of pi x, and then all of that is squared. So I want you to notice there's actually 3 layers this time. Pi x is itself a function. That is now inside of cosine, and the cosine of all of that is all squared. Okay? So when I make my substitutions, I like to start with u being the part that's the most interior part, which in this case is pi x. Now I'm going to create another variable v and call that the cosine function. It's going to be the cosine of u. So far, v is the cosine of pi x because pi x can go in here where u is. But now that is all in the squaring function. So my main function is y equals, and then I'm going to have v squared, because that way, if I combine all these down, it's going to become what I started with. Pi x goes into the second one where u is, so now it would become cosine of pi x. Now, if all of that goes into here where v is, I have the starting expression. Okay, but this time, to find dy dx, it just requires 3 links in the chain. I've got to find the derivative of y with respect to v, and then v has a derivative in terms of u, dv du, and then finally I can find the derivative of u with respect to x. And the fortunate thing is all 3 of these functions have simple derivatives. The derivative of y with respect to v is simply going to be the power rule. So it's going to be 2v to the first. And then the second one is the derivative of v, which is the derivative of cosine. So that's going to be negative sine of u. And then finally, derivative of u with respect to x. Well, pi x is really, pi is a constant, remember, so you know, if it was 2x, the derivative would be 2. So if it's pi x, the derivative is pi. Now the only thing left to do is bring this all back in terms of the variable x. So for v is the cosine of u, but then u is pi x. So 2v is really 2 times the cosine of pi x. Negative sine of u is negative sine of pi x. And then we're multiplying by pi. So the only thing really to do is maybe bring all the constants to the front. There's a 2 that's already there. There's a minus 1 in front of the sine of pi x, and then there's a pi here. So if I brought 2 times negative 1 times pi, the coefficient is negative 2 pi, and then we would just have cosine of pi x sine pi x. And that's how I would leave my answer. So y prime equals. It's good to practice every so often with a chain rule problem that's got more than just 2 layers. So this one's got 3, and it's a good way to practice your use of the chain rule. The other ones I thought we would take a look at involve exponential functions. So these are all just the chain rule version of this basic rule. The derivative of e to the x was e to the x. So if there's more than just x here, it needs to be considered e to the u, and then we just use the chain rule. Use the basic rule, and then multiply by the derivative of the inner function, and that's u prime. So in the first one, I can let u be the expression 2x, and then the main function is y equals e to the u. So my derivative is e to the u, u prime. And I'll just fill it in. E to the u is e to the 2x. U prime is the derivative of 2x, which is 2. And if you prefer to write the 2 in the front of all of it, it's 2e to the 2x. Just like that. I'll work out the second one. Then I'd encourage you to pause the video and try the third one. So in number 2, I would let u equal negative x, and then the main function is 2e to the u. This is just a constant multiple, which does not affect the derivative at all. So y prime is 2e to the u times u prime, and we fill it all back in. This is going to be 2e to the minus x, and this time u prime is the derivative of minus 1x, which is going to be minus 1. So my final answer, I would probably combine 2 times negative 1, make this negative 2e to the minus x. Final answer. I encourage you to pause the video here while I work out the last one. Maybe try it yourself as well. So here's my last example worked out. If I let u equal x squared plus 3x, then the main function is in the form y equals e to the u. So the derivative is e to the u times u prime. So that makes it e to the x squared plus 3x again. And then times u prime. The u prime would be 2x plus 3. I'm choosing to write that in the front and just put it in parentheses. Please notice the parentheses are required here. They're not optional, so that you're multiplying the entire derivative times the entire exponential expression. Okay? Without the parentheses here, it would be wrong. Okay? Well, good luck. You should probably work on up to about number 15 on your assignment sheet so far, and then we'll see you back next time to finish this off, where we'll be talking about how to find the derivative of a logarithm function. We'll see you back here in a couple days.